In this video, we're going to look at the question B of 2023, section 2 of question 3. So, it says in 1783, the Montgolfier brothers hot air balloon freely ascended but remained at a low height. So, the balloon had a volume of about 2,000 cubic meters and then a lifting capacity including its own weight of 830 kilograms. The air inside the balloon was heated by a fire in the basket below. Estimate the temperature of the air in the balloon. And then it gave us the air density, the pressure, and then the molar mass. So the molar mass of air. So I think basically we have to set an equation between the weight of the entire balloon and the buoyancy force. So the weight of the balloon would consist of the 830 kilogram of its own weight, and also I suppose the heated air inside the balloon, and then it has to it has to cancel out with the buoyancy of the air acting on the balloon. So I suppose what we can do is that the question wants us to calculate the temperature of the air in the balloon. So I think we should start off with calculating the weight of the expanded air. That is, I think that will be a viable approach. So we say that the weight of the air, let's say just a W air, and it is equal to the buoyancy force. So the buoyancy force will be rho GV, which is in this case 1.23 times 9.81 times 2000, I believe. Yeah, so density and then the volume, and minus the weight of the balloon, which is 830 times 9.81, and that should equal to times that is 15990.3 newtons, and then I think we need to calculate the mass, because in order to calculate temperature we need to make use of the ideal gas equation given the molar mass. So the mass will be equal to this divided by 9.8, so that's just and then divided by 9.8 and 9.81. Now that is okay, that is a whole number, and then it's in kilograms. Now the number of moles of air, so that will be equal to, it's given that 0.029 kilograms per mole, so that's 30 over 0.029, which is around, that is 56206.897 moles. And then the ideal gas equation, so PV is equal to nRT, and now in this case we know the number of moles we want to calculate T, so T is equal to PV over nR. And then the pressure, the pressure in this case wouldn't change, because the pressure of the expanded gas inside the air, inside the balloon, should cancel out with the pressure of the air outside balloon, or else the balloon will either expand or be shrinked. So it has to be equal to the atmospheric pressure. And then that is and then times the volume, which is 2000 over the number of moles, 0.897 times the ideal gas constant, and then which is equal to this is 1, and then you time it by 2000 over, this is 56206.897, and time by 8.314, and now that is 432 point, I'm going to leave a 432 and then I suppose in kelvins. So, and then that will be the answer to the question.